All right, a couple of announcements. As a reminder, sign up online at berkeley.edx.org for this class. That's our web presence. It's through edx.org. That's where everything gets posted about this class. For discussion, we use Piazza, so make sure you sign up there too. If we feel like we need to blast the class, we'll do it through Piazza. Then, Project Zero is already out. Many of you already submitted it. It's due tomorrow at 5 p.m. There's one more lab office hour tomorrow, 11 to noon in 271 Soda, so stop by there if you keep running into trouble. The lab is optional, but the project is not. It'll count towards your grade. There's a math self-diagnostic. This is optional, but you really should do it because only 6 weeks into the semester will we start doing more serious math. And you want to check now that you're prepared for that. Starting next week, there will be sections. You don't need to sign up for a section. There is no section sign up. You just go to whatever time slot you prefer. If it's overcrowded, we'll report which ones are overcrowded and so forth, and you can switch the next week to another one. Sections are not mandatory, but the material covered in section is mandatory. We cover material that we'll ask questions about. Handouts will be posted online. The questions as well as the solutions. Whether you want to study them in sections, solve problems with your friends to learn the material, or rather do it at home, that's up to you. But we encourage you to at least the first couple of weeks come to sections, see what you get out of it, then make a decision. One of the big things we try to do in this class is to make you already study the material before section. So your homework will be due on Monday night, and section that week will be about the same topics that you covered in homework. We've seen that the consequence of that is that everybody who comes to section is prepared, already knows something about the material because they already solved the homework on it, and we can do some more advanced exercises in section. That doesn't mean there's no time for questions. There's still time for questions and so forth. But the section problems often will be harder than the homework problems and more representative of what you might get on the exam. That's the idea here. Okay. There is nothing like your own section. That's a typo. You don't own any sections. You just go wherever you want, and hopefully it works out. Instructional accounts. You don't need them, except if you want to use the lab machines. So that's the only reason you might want to have an instructional account is to log into the lab machines. I have more of them here. There'll be more of them in the lab tomorrow. So if you don't have an account yet and you want one, we have more. Any questions about logistics? Okay, let's start with our first real topic then, search. So what we're going to look at today is agents that plan ahead. Remember from last lecture, the cartoon of the brain where there were two ways of kind of making decisions. One way is memory-based, which we'll see at the end of the semester, machine learning. The other way is by simulating in your head what would happen. That's what we're going to start looking at now. We'll call them search problems, which is a formalization of this type of problems. And today we'll cover the first three solution methods for these problems. Depth-first search, breadth-first search, and uniform cost search. So let's first think about what would be a way to program an agent to do something, right? Why do we want agents that plan? Think of this problem here. Let's say you want to program a little robot to collect apples. And one simple way to go about this would be to write some piece of code that says something to the extent of, if there's an apple nearby, move in the direction of the apple. And then you might get some of the behavior you see over there, and your agent moves towards the apple, actually doesn't get there, and then falls down the cliff. Another way to try to do this, rather than trying to code something very simple like that, is to say, well, I want this agent to think about what would happen and come up with a more complex plan. And it's not directly moving to the apple. It's actually going away first, finding a tool, and then using the tool to grab the apple. All right, it requires a lot more reasoning from the agent side, and so the program's going to be having to do something different than just you writing some rules, say, if apple close by, move towards the apple. So reflex agents are in some sense the simplest types of agents. Those are the naive agents where you just try to write down a set of rules. You look at what the environment is like right now, what the state of the agent is right now, and based on that, you have maybe some if-then statements, say, if apple nearby, move towards it. If a food pellet nearby, move towards it, and so forth. the kind of technical definition of a reflex agent is that a reflex agent doesn't think about the consequences of its actions. It just looks at the world and maps somehow from the world to an action. This can be really complicated to write code for, and that's why we're not going to be looking at these for a long time. But this is the most natural way. If you were to just write a piece of code, that might be the way you'd start out. And so we want to look at them briefly to contrast them with what we're really going to do. The first question you can ask yourself about these reflex agents is, can they be rational? Can they maximize the expected utility? Who thinks they can be rational? A couple of people think they can be rational. Who thinks they can be rational? A couple of people think they can be rational. Okay, let's look at an example. So let's look at the first demo here. This is a reflex agent that we're going to see in action here. So what do you see here? Pac-Man. Pac-Man is programmed as a reflex agent. At every time, it looks for the closest dot and moves towards the closest dot. So right now, there's a tie-breaking thing, but it'll tie-break off to move to the right. And then after that, keeps going to the closest dot. That's it. So can you do any better than that to eat all the dots? Not really. That's the best you can do. No matter how hard you think, no matter how hard your program might think about the situation, the best plan is going to be to go around the loop and eat all the dots. So what we see here is a rational agent that was programmed by programming a reflex agent. So reflex agents can be rational. Now let's look at another situation. A little more complicated. The same reflex agent, all right? So just trying to move in the direction of the closest food dot. This is not showing very beautifully, though. Let's play with another player. So this is a more complicated maze, a lot more dots. Again, the agent is going to move to the nearest dot, meaning whatever direction the nearest dot is in, it'll take the action in that direction. Taking the action east, 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 over and over and over again, and it's just stuck there. There's no way to reason about that. It doesn't reason about the consequences of its actions. It just says, let's move to the nearest dot. It's east, so let's take the action east. So here's an example where a reflex agent is not rational at all. It's a really bad strategy. So in very special cases, they can be rational, usually the simpler cases, but in more complicated environments, it's really hard to program a reflex agent to do the right thing. So we're going to look at something called planning agents. And the idea there is that you reason about what would happen if you were to take a sequence of actions. And you might reason about many possible future sequences of actions and then pick out the best one. What you need for that is a model of the world. It's not enough you don't have any rules from the current situation to an action. You need to have a model of the world that allows you to simulate, if you were to take an action, what would the world be like at the next time? You need some kind of goal test that declares success. If after taking a sequence of actions, you reach a certain situation that's good enough, that'll be your goal. You say success, so that sequence of actions is good enough. There are two types of planning agents. In fact, 4 types, whether they satisfy these properties or not. They can be optimal or not optimal. They can be complete or not complete. A complete planning agent is one that if there exists a sequence of actions that achieves a goal state, it will find it. An optimal planning agent is an agent where whenever it finds a plan to a goal state, it's always the optimal plan, and that is the plan that incurs the minimal cost to reach a goal state. So it's a more stringent requirement. Then there are 2 types of agents that you'll be implementing in your project 1. Pure, just make a plan ahead of time, execute it, versus make a plan, execute it, then after you executed some actions, look what the world is like, replan, and keep doing this over and over. So in a replanning agent, you execute only part of what you really want to achieve. Maybe in a replanning agent, your goal is to eat 1 dot. And then after you did that, you replan, and again your goal is to eat 1 dot. If you keep repeating this over and over, you'll have eaten all the dots, but you consider them 1 at a time. A full planning agent will have as a goal to eat all the dots. So let's look at an example of what that looks like. You have the same problem as we looked at before, but now with a planning agent that plans to eat the next dot. Once it's executed those actions, replans, keeps going. And it's very fast. It doesn't take very long to plan for eating 1 dot. And it cleans out the entire board. Maybe not in the optimal way. You saw it went into that dead end and it had to come back out. We're spending a lot of time not eating dots, but it does eat all the dots in a reliable way. Now let's look at the Mastermind Pacman agent. Mastermind Pacman tries to find the optimal path to eat all the dots. It's willing to spend a lot of time at the beginning to plan out this path because it's a very complicated planning problem. So we start Mastermind. It's pre-computing some stuff before it's willing to start planning. Then it's computing, simulating different sequence of actions to see what the consequence would be. It's considered 1,000 possible states. It's considered 2,000 possible states. Found the plan, and now it executes. And the execution of the plan, if you look carefully at this, there's not a single step that's going wasted. Oh, that's not pretty. So let's watch that again. Still in its thinking phase. Oh, it's not collaborating. Let's watch it in a pretty mode. Let's give the thinking. So note that it cleverly skips over that dead end and does it all the way at the end, so it never has to backtrack and waste time there. So this is the optimal way of eating all the dots, the minimal amount of time spent eating dots. So that's the kind of agent we're really after. If we can get that working, we have optimal agents that are complete, then we can solve any kind of planning problem. So one step in solving this kind of problems is to look at your real problem and to abstract it into something that we call a search problem. And the idea here is that, and this will come back and back over almost all lectures, is that we're not interested in solving a Pac-Man problem per se, or a finding apples problem. We're interested in abstracting away from those problems, get a generic structure that a lot of real-world problems can be abstracted into, and then finding algorithms that will solve those abstract problems. And then when you run into a real-world problem, you already have the algorithm that can solve all search problems. You just have to encode this real-world problem into a search problem, and then your algorithm will solve it. So what is a search problem? We'll need a state space. For the Pac-Man eating all the dots, this would be all possible configurations of Pac-Man on the board, and there might be food or not food in every position. A successor function. What that does is says, given a certain state, what are the actions available? And for those actions, what are the next states that you would land into? If there's cost associated with your actions, then those will be associated with these actions in the successor function. So in this case, Pac-Man could move north or east, each with a cost of 1, and it shows what the next state is. Then there's a start state. This is where you'll start out as an agent, and a goal test. It says goal test rather than goal state. What that means is that it's possible that there are many states that satisfy what you want to achieve. And so there will be a test, for example, for eating all the dots. The position of Pac-Man at the end doesn't matter. What matters is that all the dots have been eaten. So there are many, many states that satisfy the goal test. All the ones where all dots are gone, independent of where Pac-Man is sitting. Then the solution our algorithms are supposed to return is a sequence of actions that, if our algorithm is optimal, will return the optimal sequence of actions to achieve one of the goal states. Okay, so these are models of the world, and so we're making assumptions. That's important to keep in mind. And how you make assumptions will affect what you get as a solution. And part of the game is to come up with a good set of assumptions such that you have a fairly small search problem, but it still captures all the relevant aspects of the real-world problem. So here's an example. Traveling in Romania. This is a routing problem here in Arad, and you want to get to Bucharest. So Arad is over here. You want to get to Bucharest. In the real world, there's a very complicated problem. There's other cars. There might be birds flying over you. There might be traffic lights. There might be road construction and so forth. A lot of stuff could be going on. The abstraction we present here is one where we say what matters is the cities, and we assume that we have some action available to us that routes us from one city to another city for the ones shown here. And then the problem becomes one of finding the sequence of cities that we have to go through to get to Bucharest. So the state space here is cities. Successor function is, for a given city, what are the neighboring cities? And the cost is the distance to reach those cities. The start state is Arad, because that's where we're starting off. The goal test is, whether we have reached Bucharest. And then the solution would be any path from Arad to Bucharest is a solution. So what goes into a state space? Let's look at a couple more examples. Here we have a Pac-Man game situation. And let's say our problem is going to be pathing. So the goal is to find a route for Pac-Man to go from an initial state to a goal state, where the goal state is just a new set of coordinates for Pac-Man. Well, given that all we care about is the coordinates of Pac-Man at the end of the execution of the actions, we could say, well, as states, we just take the XY location of Pac-Man. We don't include where the ghosts are. We don't include where the dots are and so forth, because all we care about is Pac-Man moving. The actions available are to move north, east, south, west. Then successor function would update the location of Pac-Man. That's it. That's all we need to keep track of. And then the goal test would be whether x, y coordinates of Pac-Man now match the end location that we're looking for. So that's a very small search problem with regard to the entire world representation, because we have abstracted away a lot of factors here into a much smaller search formulation. How about if the problem is eat all the dots? Well, when we eat all the dots, we need to keep track of where there are still dots. If we don't keep track of that, then there's no way for us to test whether we achieved the goal. Right? So we cannot get away with just Pac-Man's location as a state. We need Pac-Man's location and all the locations where there are still dots. So you could maybe have for every location a Boolean, and it could be 0 if there's no dot anymore, 1 if there's still a dot. The actions are still the same. Pac-Man has 4 directions to move in. The successor function now has to update the location of Pac-Man and potentially update this bit about whether there's a food pellet or not in the location Pac-Man just arrived at. Pac-Man arrived at a location where there was a food pellet before, it gets eaten, and that needs to be updated. It's gone now. Then the goal test would be, are all the dots gone? Okay, so those are 2 examples. Let's start looking at how big these state spaces can be. Here, we have a new situation. Pac-Man can be in 120 positions. The food count, there are 30 food pellets. The ghost could be in 12 locations, and the agent could be facing north, east, south, or west. So that's the full world state. That's what we start from. Then, how many world states do we have? Well, we can count it up. We have 120 agent positions, so that's 120 possibilities there. We have a food count of 30. The food could be there or not be there. So that means 2 to the 30 possibilities for that. Then for ghost positions, there are 12 positions for each ghost. So we have 12 to the power 2. And then the agent could be facing in 4 directions. So this is how many world states there are. This is very, very large. Now, How many states for pathing? If what we care about is a pathing problem for Pac-Man. Well, if what we care about is pathing, the agent position still matters. Then the food count doesn't matter anymore, so we can get rid of that. The ghost positions don't matter anymore because they will not interfere with Pac-Man. And the direction the agent is facing doesn't matter anymore. So if we know the problem is one of pathing, we end up with just 120 states in our search problem formulation. What if the problem is eat all the dots? Well, we still need to keep track of Pac-Man. We now need to keep track of all the dots. We don't need to keep track of the ghosts because they can't get anywhere near Pac-Man. And then we don't need to keep track of which way Pac-Man is facing because it doesn't affect where Pac-Man can move next. So we have this many states for eating all the dots. This is still a very large number. And a big part of what we'll be looking at in this lecture and next lecture is how to efficiently deal with large state spaces, finding solutions in these large state spaces without having to enumerate all possible states, because often that's just not practical. Is there a question there?
About the keeping track of the ghosts, why not all pack one and get
Okay, that's a great suggestion there. The suggestion is, instead of 12 to the power 2, let's make this 12 times 11. If we know ghosts cannot be in the same position at any given time, then that will be enough. And that's correct. So if you know that that's the case, you can reduce your count by a little bit there and get 12 times 11. Any other questions? Okay. Let's do a quiz then. Same Pac-Man environment, as we've seen before, but a different problem. The problem now is one where you want Pac-Man to eat all the dots while keeping the ghosts scared at all times. So whenever Pac-Man eats one of these power pellets, one of the big white dots, what happens is ghosts go into a scared state for a certain amount of time. And the goal here is to solve the problem that you reach the goal state if you traverse the sequence of states where the ghosts were always scared and you've eaten all the dots. All right, take a minute to talk with your neighbor and try to figure out what a good search problem formulation would be for this problem. All right, let's see what everybody came up with. Anybody wants to explain what their formulation is? Here, yes. If you keep them scared, we assume there's no interaction. So the suggestion here was all the dots, whether they're there or not, power pellets, where they are and whether they're there or not. That's a lot of information we need. It's not everything, though. We're missing something. Yeah, so the suggestion there is you need to keep track of how long it's been since you ate a power pellet. because that'll affect when you need to eat one again, when the ghosts become unscared. Now we're missing one more thing. So how long it takes you to traverse each section, that could be one way to do it, but that would be a pretty complicated representation. What we're still missing is the position of Pac-Man, right? So what we need is 4 things. We have Pac-Man's position, booleans for each of the food dots, booleans for each of the power pellets, and then the remaining scare time on the timer for whether the ghosts are still scared or not. What this illustrates is that in the past couple of examples we've looked at, that the real problem you try to solve affects in a very substantial way what your search problem will be. And a lot of thought and practice will actually go into abstracting your real-world problem to a search problem. Because once you've implemented the search algorithms that we'll cover in the next 2 lectures, those are never going to change anymore. It's your abstraction from the real world to your search problem that's always going to be different. And that's where you're going to have your creativity and intuition. Question there. Yes, the position of the ghost is not needed because we assume that we keep them scared at all times. And so, if you're always scared, they're not going to eat you. Yes? So that's a good question. The question is really about how do you represent these dot booleans? What does that mean to have that in your state? And there's many ways to encode that. You could encode it as a list of where there are still food pellets, so a list of coordinates of where there are still food pellets, or you could have, in some sense, an assumption of what coordinate is associated with each entry in your vector, and then the first entry in the vector would be the top left corner, and then the bit would just say whether there is still a food pellet or not. So there's 2 different ways of encoding that, and there's others. And in fact, how you encode it doesn't matter too much in these problems. What really matters is that you abstract your problem in a way that you don't make the search state space too big. So whether you have a slightly bigger representation because it's a list, or whether you have a bit vector, is probably not going to affect the outcome. But if you put in, let's say, locations of the ghosts and maybe other information where direction Pac-Man is facing, that's when your search problem will really blow up because you introduce more states. Other questions? Yes? Okay, so that's a great observation. The observation is that you're saying, in the real world, if you play this kind of Pac-Man game, once Pac-Man eats a ghost, they come back unscared. All right? And so if you don't model that, and you don't have the position of the ghost in your state, then you can't model the fact that you're eating them and that they come back unscared. So if we're in that situation, we need the position of the ghost in our state. You're absolutely right. For now, we here made the assumption that if a ghost gets eaten, it remains scared. But if you're not willing to make that assumption, then your representation would be better. Any other questions? Okay, so that was our first search space formulation. Now let's start thinking about what the representation is underneath, right? What is this search problem? In some sense, there's a graph associated with it, which we call the state space graph. For Pac-Man, it could look something like this. And what is this showing to you? It's showing a lot of possible states Pac-Man could be in and where the food pellets could be and how they are connected. So a successor function in this graph is encoded for this state. The successor function is saying you could go there or there. Those are the 2 successor states. And for every one of the states, the arrows going out indicate what the successors are. Now, the nodes are the states. Arcs represent successors. There will be some test for each. When you feed in a state into that test, the test will return true or false whether the goal is satisfied or not. In this search graph, every state will appear only once. This is going to change when we look at our algorithms. But in the original formulation that we start from, the search state space graph, every state appears only once. Rarely, if ever, are you able to build this graph. In this lecture, next lecture, we'll show state space graphs on the slides. That's just to illustrate how these things work. If in reality, the state space graphs were so small that you could put them on a slide and see what's in them, then the problems are so easy that there's no reason to write an algorithm to solve them. You could very easily solve them by just looking at them and very naive algorithms could solve them. So the reason we're interested in search algorithms is because typically these state space graphs are so big they have billions, if not many more nodes, and so you can't just look at them. Okay, here's an example that we'll be using a lot. Tiny, tiny graph that we'll be illustrating our search algorithms with. This one here will be the start state. This will be the only state that satisfies the goal test in all of our examples. Now, let's assume we're given a search problem. We want to solve it. The main abstraction that we'll be using to solve these problems is something called a search tree. The search tree is something we build up when running an algorithm. This is how the search tree starts. You have your initial state, the start state. Then you can call a successor function, and you see the possible futures from the start state. And you can keep doing this over and over and over, and that way you build a search tree. If you do this, and it's possible for Pac-Man to go around in a loop while not eating any dots, you will see the same state coming back and back and back as Pac-Man goes around the loop, deeper and deeper and deeper in the tree. So this search tree will very often have repeated states. It's just encoding what the possible futures are. Really, the way to think of this search tree is it's encoding this whole simulation process. It's encoding what would happen if I were to take a sequence of actions. And every branch down the search tree is giving you one of these possible sequence of actions that you're willing to consider. For most problems, we can't actually draw out the search tree. Even when the state space graph is relatively small, the search tree can already be very, very large. That's something to keep in mind. We show it on the slides to illustrate what's going on underneath, but in practice, the game of coming up with algorithms for these search problems is one of not needing to build the entire tree. In fact, trying to build as little as possible of the tree, but just enough that you find that sequence of actions that achieves the goal, maybe in an optimal way. So here's a state space graph for our problem, and here's a corresponding search tree. So look at state S here. S is over here. What are the successors? D, P, and E. That's what you see over here, D, E, and P, and so forth. An important thing to keep in mind with these search trees is that they don't, when you look at the state P over here, it doesn't just encode the state P. What it encodes is actually a plan. It encodes the plan to start in the start state, move in the direction that brings you to P, and then being in P. And so while P is over here and P is over here, these nodes in the search tree are fundamentally different. One of them is the plan S to P. The other one is the plan S, E, H, P. Let's do another exercise. Here is a small, tiny, tiny state space graph, 4 states. This is your start state. Start state, you can go to A and B, and then A, you can go to B, the other way around, and then there's a goal state. Try to think of what the search tree looks like for this state space graph. And we'll take a half-minute break. You can talk to your neighbors or just think about it on your own. Think about what the search tree would look like and how many nodes it'll have. Okay, let's see what people came up with. How many nodes in the search tree? Right here. Infinite. Who agrees with infinite? All right, fantastic. Right, what's going on here? Search tree, S. S to A, S to B, A to B, could also go to G, B to A, could also go to G, B can go to A or to G, and so forth. So this keeps growing forever. So even for this very small state space graph, you have a huge search tree. So you really don't want to explore the entire search tree to then find your right path. Let's look at this example again here, search example, and let's solve it. Let's build a search tree, solve this problem. So how do you do that? You start with the start state, arad. What's in green doesn't exist yet when you're running your algorithm. You just have the start state. We don't want to build the entire search tree, so what you end up doing is you say, well, let's look at the successors of arad. What are the successors? Well, there are 3 successors. You grow your search tree. Now you have a slightly bigger search tree. And then you pick one of these successors, and you say, well, let's expand from that successor, and keep growing the search tree one step at a time. And somehow you hope that you'll guide the process of expanding the search tree in a way that you somehow find the goal state relatively quickly. And once you find a goal state in the search tree, you also have an entire path. So you have a plan to get there because the search tree encodes that too. This will be our game, is to expand as few tree nodes as possible. Okay? So here's generally what this algorithm looks like. Tree search. You pass in a problem, that's a search problem, and a strategy. For now, let's not worry about the strategy. You initialize your search tree using this initial state of the problem. Then you loop. You keep going around this loop until you somehow have success. Whenever that happens, if you have a node that contains a goal state, you're ready to return and return the solution that corresponds to it. But what you're doing in this loop is you check, is there any candidates for expansion left? Like at the bottom layer of your tree, which we call the fringe, the nodes you haven't expanded yet but have already considered to put in your tree. Check if there's any of such nodes left. If there are, then you pick one, you decide to expand it by calling the successor function, and put things into the tree. If there's no such nodes left, that means that you're in a dead end everywhere in your tree. There's nothing left to do, and there's no solution. So either there's no solution, or you keep going, keep expanding, working down in the tree, picking a node from the fringe, expanding it, and so forth, until you find the goal state. What are the important ideas? You keep track of a fringe. You expand nodes in that fringe, one at a time, one in each loop. And then you put all its children into the tree. And you have a choice there. Your fringe will consist of many nodes, and you have a choice there. That's your strategy to decide which one to expand first. So let's do this and use our own strategy for now. So we have a search tree, a state space graph here, state space graph. And let's do the search, and I'll do it in 2 ways at the same time. I'll build the search tree, and in parallel, I'll build another data structure that is often the data structure you'll code this up with, which is a priority queue. So we'll have 2 representations, search tree, which you already know about, and then a queue over here. What do we start with? We start with the initial state, S, and the queue will be initialized with just S. That's our fringe, or queue or fringe, is shown here. Well, only one node in the fringe, so that will be the one we have to expand. We have no choice. So we pick S, we expand it. The successors are D, E, and P. So we have D, E, and P over here. What happens in the fringe is that S gets removed from the fringe, and instead we now get S to D, S to E, S to P. Now, our fringe consists of 3 nodes. We pick one for expansion. Which one do you want to pick? E. All right, let's go with E. We expand this one over here. This one here. We already expanded S. Now we expand E. What are the successors of E? H and R. So we have H and R. Over here, S to E disappears from the fringe, and we get S, E, H, and S, E, R. Which one do you want to pick next? R? Okay, let's pick R. What are the successors of R? Just F. So we expanded R. R is over here, and now we have instead S, E, R, F. All right, which one do we pick next? F, okay. F leads us to G. Here we get S, E, R, F, G. Which one do we pick next? C? C is not even in our fringe as far as I can tell. That's not an option, C. Should it be? Did we miss one? Should be in our fringe. Let's add it. S, E, R, F, C. So which one do we pick next? The majority picks G. Sorry. We're going to go with G. Pick G. What happens now is we pull a node from the fringe. The last state in that node is a goal state. So we declare success, and we found the path to the goal. Now, it might have seemed a little quirky that once I put G on the tree, at the bottom of the tree, that I didn't declare success yet. And I said, well, you just put G on, why don't you just stop, call it done? It'll turn out that it's really important that you don't declare success when you put things into the tree, but that you wait till you pop something back out. That'll later give us optimality guarantees for our algorithms. Waiting till you pop something out to be willing to declare success is going to be really important. Okay, this was what we call 188 guided search. This is available to you if you're a professor and lecture. If you are programming something, you don't get a body of students to tell you what the next state to expand is. You can't do this. So what we're going to do in the second half of lecture is look at different strategies where we will have the computer automatically decide what the next state is to expand. So let's take a couple minutes break here, and then we'll look at the different strategies. Okay, let's start looking at search strategies then. The first strategy we'll look at is depth-first search. Depth-first search goes down the search tree as deeply as possible right away. So it digs straight down. This is a reasonable cartoon, good way to remember it, but keep in mind for real search problems, the size of the tree, the number of nodes that are sitting further below grows exponentially with the depth of the tree. So the deeper you go, exponential growth. So there's a lot of nodes at the bottom. This is not really pictured here because you only have 2D. Even if you had 3D, it wouldn't grow exponentially. You need something that we can't draw to show that exponential growth, right? So keep in mind the bottom of the tree is very, very big. And depth first goes straight down some paths in the tree straight to the bottom. So see what it looks like. We have the same problem we were looking at, a start state. I've already drawn the search tree. I've circled the nodes that are currently on the fringe. What will depth first search do? Well, D, E, and P are equally deep. So the strategy doesn't tell you what to do. You need to do tie breaking. We'll do tie breaking alphabetically, so we'll go with D first. So D. Now what are the deepest nodes? B, C, and E, where it's specifically these three here. We'll do alphabetical tie breaking. We'll get B to expand first. Now A is the deepest one. Try to expand A. No children, so we're kind of at a dead end there. Now the deepest ones are C and E. Alphabetically, C is first. Go with that. We again encounter A. Again expanded. Has no children. Go to E. Keep going. And the pattern you see here is some kind of left to right striping through this search tree. Let's look at this again. What you see is you start here and you see highlighted paths left to right all the way till the bottom of the tree until you reach the goal state. You expand the goal state. You try to expand it. You realize it's a goal state. You say, okay, we declare success. We found the path to the goal. So this is the path found by depth first search, and it explores this part of the tree. So depth first search will, in this case, have seen these nodes in the search tree, but not the other ones. So it hasn't seen the entire search tree, which is great. Ideally, it would see even less of the search tree and find the goal, but this is what it is. Okay, so what kind of properties do our search algorithms have potentially? So first one is, are they complete? So is depth first search complete? Is it guaranteed to find a solution if one exists? That's the property we might be interested in. Is it optimal? Are we guaranteed to find the least cost path with this procedure? how long will it run before you find a solution, if there is a solution, and how much space will it take up? How much memory will you be consuming during this search? So we'll use these cartoons of search trees to illustrate the concept, but keep in mind, trees don't just grow like that. They grow exponentially in size the lower you go in the tree. There'll be a start state at the top. Then we'll have a branching factor, which is the number of children a state can have, the maximum number of children a state can have. So we have one node in the top layer, potentially b nodes in the next layer, b squared nodes in the next layer, and b to the m nodes in the bottom layer if the bottom layer is m steps deep. Solutions could be at any depth. They don't have to be in the bottom layer. Whenever you reach a goal state, it could be after 2 hops, after 5 hops, whatever your problem happens to have. So here's 2 example goal states shown in red. And the way we stripe through the tree, depth first would find the leftmost one. It would find something like this. But another algorithm might find the other one. What is the number of nodes in the entire tree? So worst case, right, the most naive algorithm would be, let's build the entire tree and then look at all the nodes and see which one satisfy the goal test, and then we find all the possible solutions, right? That's very naive, and it's very expensive. You have an exponential number of nodes in the search tree relative to the depth of the tree, so how many actions it might take to get to your goal. Okay, so let's evaluate these properties for depth-first search. What nodes does it expand in this tree? Well, as you drew in the previous picture, it'll be something like this. We'll have expanded everything that's out there until it finds that particular goal node. So some left prefix of the tree. Could be the whole tree. If the goal state happens to be sitting over here and that's the only goal state, you do the entire tree, which would be very unfortunate, but that's what it would do. So the worst case, assuming it's a finite depth tree, would be order b to the m, which could be very long. How much space does it take up to run depth-first search? What is taking space when we run these algorithms? Well, what's taking space is the fringe you keep track of. We had that fringe, right? And that's what we were looking at to see what node to expand next. And so the number of nodes that could sit in the fringe is going to determine how much memory we need. So how many nodes can be sitting in the fringe at any given time during a depth-first search? Question or answer? Answer, okay. B? So the answer, suggested answer here is B. Maximum number of nodes in the fringe is B. That's one possible answer. Another suggestion. Another suggestion is B to the M. Any other suggestions? Back there. B to the B. We're going to have a multiple choice with many options. Steven. B times M. Anything else? Yes. The fringe is the set of nodes that we are considering for expansion. So when I had the drawing, when we stepped through the algorithm, on the left was the fringe, on the right was the search tree. So it's all the nodes that are still considered for expansion. No more suggestions? Okay, who goes with option 1? Some people. Who goes with option 2? A little more. Who goes with option 3? Only the proposer. Who goes with option 4? That's a good fraction of people too. I'm going to go with option 4. Why option 4? B times M. What's happening? When you're running depth-first search, and you're at the bottom of the tree, which is, of course, when you're in a bath, let's say you're over here, you're working through your depth-first search. Let's just pick this bottom here. You're keeping track of that path, right? At that point. And one level up, you have other candidates, right? And down here you have other candidates. And up here you have another set of candidates. You have another set of candidates and so forth. At every level you consider maximally B children, but you don't consider them all at the same time. You go down one particular path. So those B children are in consideration, are sitting on your fringe, but only one of them is what you take, and you keep going, keep going, keep going. You're at M levels in the tree, and at each level at most, B could be on the fringe. So the total would be B times M. So that's a pretty good memory property, right? Memory requirements won't grow very quickly in depth first search. Time requirements, on the other hand, are exponential, which is pretty bad. Is it complete, depth first search? Who says it's complete? Okay, about half of you. That's a good amount because it's actually a tricky question. You could say yes, you could say no, and so we're right on the mark with 50%. M could be infinite, and that's the tricky part here. It's possible that you go around in a loop. Remember the initial problem where we had S, A, B, B back to A, S could go to B, and they could go to the goal. Depth first search there would go down S, A, B, 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 and never stop. So in that case, it's not complete because it would run forever, still not find a solution, but there exists a solution. We'll see in next lecture how to deal with these repeated states that come back and back and back and how to avoid them. But the way we've seen depth first search for now, it's only complete if you make sure that you don't have these cycles. Is it optimal? No. That's pretty clear, right? It's just arbitrarily striping down this search tree. Whatever is the leftmost solution is going to find. That's not by no means guaranteed to be the optimal solution. Okay, let's look at a different strategy. Breadth first search. This is like strip mining. The tree is the mountain. You kind of go layer by layer, and you check if you find your treasure anywhere soon near the top, right? So what does it look like in our search problem here? Again, the top is the state space graph. The bottom is a search tree. The circled nodes in the search tree are the ones that are currently on the fringe. So initially the fringe just has S. So that's our only choice for expansion. We get 3 children that go into the fringe, D, E, and P. Keep in mind they're really SD, SE, SP. What would you expand next? They're all equally deep. Breadth first search picks the shallowest one first, but they're equally deep, so tie breaking. We'll do alphabetical tie breaking. D first. Then we look at the children of D. We get B, C, and E over here. What are the most shallow ones now? E and P. Alphabetical tie breaking gives us E. We continue this process, and we see that we stripe through this search tree, top to bottom, layer by layer, until at some point, in this case it's going to happen over here, we end up expanding a node that reaches the goal state, and at that point we declare success. Nice property you can read off of this is that with breadth first search, you're going to find a path to the goal that takes the minimal number of steps from the start state, right? Because you're going to find one of the shallowest states that achieve one of the shallowest plans that achieve the goal. Okay, that's breadth first search. So what are the properties? What nodes does it expand? Well, it kind of stripes from top to bottom, so it looks something like this till it finds the goal, the highest up goal. Now, we'll introduce a little bit of extra terminology to characterize the complexity of breadth first search. S is the depth of the shallowest goal. Then it takes time to expand all of these nodes here, which means B to the S. How much space does the fringe take? What is the space complexity for breadth first search? What is on the fringe while you're running breadth first search, right? Let's say you're running a search and you're currently somewhere here. What will be on the fringe? Well, the nodes that you're about to consider, that you're willing to consider right now. What are the nodes you're willing to consider? Well, from these nodes here, you have expanded to their children. These are sitting here, right? Then this node and all these nodes here are the ones you're willing to consider now. So you get a fringe that looks like this. So the worst case fringe would be, with the goal state here, you would end up with a worst case fringe looking something like this over here and this entire stretch over here. Right? So the worst case, if the goal state were all the way to the right, you would have B to the S plus 1 nodes on your fringe, and that's the maximum you'd get ever doing your breadth first search. It's a lot more than depth first search, because it's exponential in the depth of the shallowest solution. Is it complete? Is it guaranteed to find a solution if one exists? Yes. Then is it optimal? A little subtle here. It depends on how you define optimal. In some sense it's optimal. It'll find the shortest in terms of number of actions you need to take, but if your actions might have different costs, maybe some actions more expensive if you have to go through some expensive part of the space, then it would not necessarily be optimal. It's optimal in the sense of minimizing the number of actions to reach the goal. All right, so when will BFS outperform DFS and the other way around? What do you think? Take a moment to think about that. Let's take a minute break where you can chat with your neighbor and see what you come up with. All right, let's see what people came up with. Any suggestions about the relative merits of these two approaches? Who has a suggestion? Suggestion there, yes. Say that again? One suggestion is if the tree is such that there will be cycles, and your depth first search doesn't check for cycles, then clearly BFS is going to do better, because DFS could go in these cycles and keep going forever. That's a great benefit for BFS. That's one. There's a lot of more relative merits. Yes, here.
Can I say breadth is better on everything except for the amount of space it takes up?
That's another suggestion here is BFS is better for everything, because it'll only look at the top of the tree, and because the tree goes exponentially, right? You'd imagine that you can limit how much you look at to the shallowest solution, right? Then you'd look at a lot less of the search tree, typically, and you'd find the shortest in terms of number of actions, just more memory. That is pretty close to where the merits are. There's one more subtle thing there. Yes? So one suggestion here is if breadth first search is such that it cannot keep the fringe in the cache, so the memory requirement is too harsh for breadth first search, you might really slow down, and depth first search could do a lot better. So that's related to the fact that it's worse on memory, and then it could be worse on speed because it's worse on memory. Correct. These are all important considerations. In the back there. BFS can handle variable costs for actions. That is true, but it will not find the optimal solution. It won't really account for them in a great way. The last one is something really subtle. Actually, let's have one more student answer. Say that again? So the suggestion there is really getting at the last point. It depends on how your tree is structured to some extent. What might be better? And the subtle thing there is that, and we'll see some examples of that, is that if all the goal states are at the bottom layer of the tree, all of them, then BFS, striping through it top to bottom and keeping all that stuff in memory, is going to have a big memory requirement, but not get any benefit from striping through one layer at a time. And DFS will be much quicker. Exploring all the way to the bottom, might be lucky much sooner also. And we'll see problems like that in the Fourth lecture, constraint satisfaction problems will be of that type, where all the solutions are sitting at the bottom of the tree, and then depth first search will be the search strategy of choice because we go straight to the bottom with minimum memory requirements. All right, now how about getting the best of both worlds? Actually, let's first do a demo, and then let's look at getting the best of both worlds. So what we're going to look at here is let's fast forward to 35-ish. Okay, what are you looking at here? This is a search problem. The green is your ship. Blue is water, and black is space that you can't traverse. Red is where you need to get to. That's the goal state. Now, what we're going to look at is we're going to see an animation of search in action. So we'll look at either depth first search or breadth first search. I'm not telling you ahead of time what it's going to be. And the way we'll see it in action is that as the algorithm is expanding states, calling the successor function, whenever it calls a successor function on a state for the first time, it'll put a white dot where that state is. So you'll see an expansion of white dots indicating the order in which states are getting expanded. Now, some states might get expanded multiple times, as we know. The second time it's expanded, you don't see any action on the video here. But you see the white dot pop up the first time a state is expanded. And then we'll see which algorithm you think it is. So here's a first run. All right. Who votes for BFS? Fantastic. It's BFS, right? If you look at the pattern here, what's going on is you start with start state, around the start state, wherever you can reach from there. Of course, the black obstacles block it in some places. You stripe out uniformly from there and then reach the goal. All right. Now let's take a look at another one. Maybe it's BFS again. Maybe it's DFS. Let's see what you think. All right. Who thinks DFS? Great. It is DFS, right? You see what it's doing is just kind of going depth first, not striping out in some kind of radial fashion. Instead, just going in the direction it started out and finding whatever it can find in that direction. How about getting the best of both worlds? There's this thing called iterative deepening. We're covering it now, but later when we see other algorithms that are a lot like BFS, there will be iterative deepening versions of those other algorithms too. The idea is that we want something like BFS because we want to find the shallowest solution, but the memory requirement of BFS is terrible because you're keeping the entire current layer in the tree in memory, which is a lot, exponential in the depth of the search solution. So how do we do that? Here's the idea. You run a depth-first search, which we know has not a whole lot of memory requirements, so it can be very fast in terms of memory, no problem there. But you only run it to depth 1. So you don't expand any states if that search node is deeper than depth 1. If you find a solution, great. You found a depth 1 solution, you're done. If you don't find a solution, you again run depth-first search, and now you pass in the parameter maximal depth 2. Find the solution, great, you're done. You found a depth 2 solution. It'll be the shallowest depth solution because you tried depth 1 before. And you keep repeating this until you find a solution. You're repeating some work, obviously, but you do have the property that this way of repeatedly running depth first search, A, you get the limited memory requirements from depth first search, and B, you get the optimality in terms of number of actions to get to the goal from breadth first search. How about that redundant work? Is that a big problem? Striping through the tree multiple times. Here's where it's important to remember that this tree grows exponentially. So exploring the bottom layer of the tree is a lot more work than exploring any of the previous layers. So the fact that you do some shallower tree explorations first actually barely affects your total running time. Your total running time will be dominated by the deepest run that you're willing to do. And so, yeah, it's a little bit of extra work, but it's not a whole lot. It's negligible compared to the last run. What's the question there? Yes?
Would it be better if you did, like, sort of save the first few rounds?
Okay, so a suggestion there, how about caching? That's a good suggestion. If you can cleverly cache the right stuff, that's great. But if your memory requirement goes up because of the caching you're trying to do, then you're going to run into problems, right? If you want to cache the entire last layer, then you're back to the memory requirements of breadth-first search. Yeah, that'd be a great optimization. Cache until as much as you can, but keep in mind you need some space in your cache for other things still, right? Any other questions about this? Okay, so best of both worlds. Now let's move on to search where there's a cost. What's different in this graph is that now every action has a cost associated with it. Cost 3 to go to D, 9 to go to E, 1 to go to P. Breadth-first search will not find the lowest cost solution. It will find a solution with the minimum number of hops. We want the lowest cost solution now. How do we do that? Well, when you're going down this search tree, if there's something very expensive to go through, like a big rock, you avoid it initially because that takes a lot of time, very costly. That's the idea for uniform cost search. So let's look at uniform cost search in action. Same problem. Again, initially, this is on the fringe, and that's it. We expanded, only one on the fringe. We now have 3 nodes on the fringe. We now pick the one with the lowest cost so far. That is P, cost of 1 to get to P. So P goes first. We put its children into the fringe, which is Q. Now what's the lowest cost one? D, cost of 3 total. We go with D, put its children on the fringe. Now we look at the lowest cost one, B, cost of 4. Now it's E, this E over here, which is the SDE plan. Expand that one. Now A, which would be over there, dead end, no children. Now R, then F. At this point, I'm going to make this remark again because the most common bug in your project 1 to do this wrong is we now have a fringe. On the fringe, there is a node that achieves the goal, but we don't declare success yet. We just keep running our algorithm. We say, let's pick the next one from the fringe according to the criterion of which one has the lowest cost. It's not G, it's actually this one over here. It's E. SE goes next. At this point, G is the lowest one with 10, and we can declare success. We found a path to the goal that is actually guaranteed to be the lowest cost path the way we run this procedure. So this is the path we found, SDRFG. In breadth-first search, we had this striping through the tree, layer by layer. Here we're still striping through the tree, layer by layer, but we explore nodes in the order of the cost. So first, all nodes with cost 1, then all nodes with cost 2, all nodes with cost 3, and so forth. So a different shape of the striping, but we're still striping through the tree in some top-down fashion. Let's look at the properties of uniform cost search. Actually, while we're at it, one thing to keep in mind, uniform cost search. The costs are not uniform. All actions have different costs, typically, right? So what it means, uniform cost is not that the costs are all the same. What it means is that when you go through your search tree, you stripe cost 1, then cost 2, and so forth. So it refers to the procedure, not the cost on the actions themselves. So what nodes does it expand? Let's say, you work through this tree, you find a bunch of nodes, you find the goal. At that point, you have expanded every node that has a cost less than this goal node. Because if it was anything with cost less than the goal node, you'd pull it out first before you'd pull out the goal node. So we introduce a little bit of new notation, C star. C star is the cost of the cheapest goal that you can achieve. Epsilon is the minimum cost of an action. That's an assumption we make. We introduce this epsilon. Now we can say, how deep is this cheapest goal? The depth of that cheapest goal is at most C star over epsilon. So that's the maximal number of actions that we've taken, maximal depth of the tree. So the amount of work we do is similar to breadth-first search, but rather than the depth of the solution, we now have this C star over epsilon, which is the maximum number of actions that you might take until you get a total cost of C star. So B2, maximum number of actions until you end up with a cost C star. How much space does it take for the fringe here? This is very similar to breadth first search, right? You're keeping this fringe around with anything that's cheaper that you haven't expanded yet. So this is order exponentially again, b to the c star over epsilon. So b, which is the branching factor, maximal number of actions for any state, to the power maximal number of actions until you reach a cost c star. We'll never have more actions than the number of actions needed to reach cost c star, because by that time we would have found the goal state. Okay, is it complete? Guaranteed to find a solution? Actually a little tricky. If there is a minimum cost, epsilon, for every action, then it is guaranteed to find a solution. But if there's no minimum cost, you could go down really weird trajectories, where it's something where it says, cost of this one is, let's say, 1/2, then 1/4, then 1/8, then 1/16, and so forth. And so it keeps actually growing very, very slowly. You could go down very, very deep branches in the tree with very low cost. So for it to be optimal and complete, we need this minimum cost per action epsilon. Is it optimal? Yes, right? It finds the minimal cost way to reach the goal because it has looked at everything that's cheaper by the time it declares success for the goal. We'll see a more formal proof next lecture when we see a more general version of this. Let's continue here next lecture.